Thank you, Helen. And good morning, everyone. And hi to everyone online. I think it's connected to online, right? Yeah. Thank you very much for joining us. My name is Shin Sugiyama, the president of International Glaciological Society. And today I am deeply honored and delighted to be with you to celebrate Helen for the Seligman crystal. I have some words before reading the citation of this award. The International Glaciological Society was founded in 1936, so it's just 90 years ago. And sometime later, in 1962, the Council of IGS decided to establish this Seligman crystal, which is awarded in recognition of outstanding scientific contribution to glaciology. And since then, so it's 64 years since this award was established, only 45 glaciologists awarded for this crystal. So it doesn't happen so frequently. We are very happy to be here to witness. And the Seligman crystal shall be awarded to a single person or collaborative group or team that has made exceptional scientific contributions to glaciology, which is defined as any snow and ice studies. The nominees' research contributions should have had a long-lasting impact on the understanding, the direction or focus of a glaciological discipline, and have transformed the discipline in a unique way. This may include opening up a new area of the discipline or radically transforming thinking in an area, and will typically include producing a substantial high-impact body of consistently leading-edge work. And now I have the citation for Helen's award. Professor Helen Fricker from Scripps Institution of Oceanography is an international leader in polar remote sensing. Her work with satellite-based laser altimetry has led to groundbreaking advances in our understanding of the dynamics of the Antarctic ice sheet. One of Professor Fricker's most significant contributions to glaciology is the use of altimetry to revolutionize the study of ice sheet-ocean interactions. She has used satellite-derived data to observe sub-ice shelf oceanographic processes crucial for understanding mass fluxes in the Antarctic ice sheet. Her research has shown that thinning ice shelves reduce their buttressing effect on glaciers and ice streams, leading to accelerated ice loss. Equally significant is Professor Flicker's use of laser altimetry to discover large active subglacial lakes beneath the Antarctic ice sheet. Subglacial lakes had been presumed to be static features of the ice sheet, but her work demonstrated for the first time that the lakes could fluctuate over rapid timescales of weeks or months. Other outstanding scientific discoveries include the first mapping of marine ice at the base of the Amelie ice shelf, and more recently, a 30-year record of ice sheet height change that has revealed pervasive mass loss across Antarctica. Such records are critical for better constraining Antarctica's contribution to global sea level rise. Professor Flicker is a generous and tireless contributor to the glaciological community. She has been instrumental to the success of NASA's ISAT and ISAT-2 satellite missions, pushing boundaries for new satellite missions, and has established one of the world's most productive glaciological research centers in Scripps Glaciology Group. She has transformed the careers of many junior scientists through her mentorship and support. Notably, the majority of her papers are first authored by her students and postdoctoral mentees, speaking to her generosity as a scientist and mentor. Her activities have extended well beyond her science to advocate for increased understanding of Antarctica and its implications for the planet, including briefing senior politicians and advisors. Professor Flicker's extensive body of work and her dedication to the scientific community have made her a leading figure in glaciology and polar remote sensing. Her innovation and insight in applying new data sources to long-standing glaciological problems have transformed how we now think about the dynamic processes shaping Antarctica. On behalf of the Awards Committee of the International Glaciological Society, Sue Cook, the chair of the committee. So congratulations, Helen.
Thank you.
Yeah,
So,
I'm so delighted.
I don't want to drop it. I still...
Please. Congratulations.
Thank you so much. Thank you. Oh, welcome. Shall I put it? I'll show the.
Maybe here.
Maybe we should show the
yeah.
audience before I drop it. Thank you for your generous words.
This is my small
so
gift
much.
from for your next trip to
Thank
Japan.
you. Thank you so much. This is so nice. I will open this later.
So
Well,
it's
that's
time
overwhelming.
to listen to you. So the floor is yours.
Thank you. Thank you so much, Shin. It's really to sit and listen to those words. It's hard to hear things about yourself, but your words were so generous and kind, and thank you. And thank you for coming all this way to this meeting, and again to all of you for coming here to this meeting. We actually had this meeting booked, as I said at the beginning, on Monday for 5 years. So I didn't know I was getting this award until 2024 and I got selected. So it just happened to be serendipitous that IGS came to me to award the Seligman crystal, which is great because it means that my family and friends can be here as well. So and thanks to everyone joining online as well. It's really nice to be able to do this. But with that said, I also know many of you, because of my English roots, are quite keen for this to be done in 32 minutes. So I'm gonna do my best, and hopefully there'll be no score if I go over time. And yeah, I'll just do what I can. We did not know about this clash either. So thank you so much, and thanks for giving me the opportunity to give this talk and tell my story a little bit. It's kind of two stories in one, sort of intertwined. Some of the things that you referred to, Shin, in my citation, I'm going to talk about actually. I hadn't seen the citation, so it's sort of a little bit like an abstract almost. But I wanted to talk about what we've learned from all of these radar and laser altimeter systems that we've had flying over Earth since the sort of early 70s or so, and give a little bit of a story there. But also alongside that, I want to intertwine my own personal story and how it all fits together in terms of where I was in the different stages of these altimeter developments and sort of the people I met along the way to lead me to where I am today. And just to sort of get to the punchline before we get to the end, right now, I'm actually the PI of a recently selected laser altimeter mission for NASA. So how did I get to that point? You'll learn that in this talk. So thank you for giving me the opportunity to do this. And I will go ahead and try and work all of this technology because there's a lot going on here. Okay. Yep, so I can't. Oh, on here. Nope. Everybody's had trouble with this. Why? Okay. Yeah, now I can see the slides. Okay, that's great. Okay, so just for context, like why am I talking about vital signs of the Earth system at a glaciology meeting? We've already heard this a little bit at this meeting, and I think, as humans living on this planet, we need to understand our role as, glaciologists don't exist in a little glaciology bubble. We're actually a part of a large interconnected system, which is our planet, that's also our home. And as we know, all too well, how do I get the movie to go? Okay. The Earth is warming. Everywhere around the world is having heat waves right now, maybe even Australia in the winter, but it does in its summer too. There's hot days all the time. The global average temperature is increasing every year with time. And because it's an interconnected system, there are many things in the system that are actually interacting with each other. And so it's not just anymore about just the ice sheets, just the sea ice, just the glaciers. It's about other things as well. And on the right here, we have a map of what we call tipping elements. They're climate tipping elements. And so these are all of the sort of entities in the Earth system that have been identified to be vulnerable to irreversible retreat should a certain temperature be breached. And so 1.5 degrees centigrade above pre-industrial is, stay close. Okay, I'm being told I'm moving too much. You knew I would though. Is where we're sort of currently very close to. And some of these tipping points will be breached fairly soon as we go into the sort of 2030s, that next decade. And this is something to be very concerned about. We need to keep an eye on these tipping points and make tipping elements and make sure that the tipping points, if they do get breached, we know where they're at. We need basically tools to help us navigate through this period of uncertainty as humanity has to learn how to live on this planet that we're warming. So the tools are super important and they have all sorts of societal relevance. And I'll talk about some of these things: sea level rise, flooding, fires, even orangutans. We'll talk about orangutans. That's probably the first time at a glaciology meeting that we've talked about orangutans, which is great. And so, yeah, as the climate's changing, we know that the frequency and intensity of extreme weather events is increasing. I think we all know that. Wherever we've been in the last month or so, we've probably felt this somewhere. And so this leads to very extreme things: heavy rainfall, drought, all sorts of things that we really have to try and adapt to. And it's kind of basically learning to live with this and become more resilient to these changes. The last IPCC report told us this. We've known this for a long time. So one of the things that people need to know about altimetry, if they don't know this, is it's not a complicated measurement at all. It's just literally the Earth's height. Everybody knows what height is. Every single person, trust me. But I'll show you right now what the two halves of the hemisphere look like with ISAT2. This is sort of a punchline, but I'll show you the movie at the end if I have time. This shows you the mean forest height, the mean terrain height, the ocean topography, the sea ice, and the land ice, all on one map, all from one instrument. And it's basically by looking at the Earth's height. I'm just going to move I need to move okay. I can see people moving on the screen. So okay. It's kind of, how do we close that? Because it's distracting me. Okay. And so we will.
Your mum's there.
Oh,
Your mum is there.
But I could just see okay. Well, there you go. That's fine. That's totally fine. It's all good. So literally everybody does this when their kids grow up. Oh my gosh. Okay. Right? You measure your height of your kids against some sort of, I don't know, makeshift thing on your kitchen wall to measure how high your kids are. This is height with time. So we're literally making this experiment as our kids are growing up, or as we grew up. You probably remember this. And this is literally all altimetry is doing. It's making a map of height versus time for everything on the planet, like whether it's a tree or a forest or a glacier or a ocean. Just how high is that thing above a certain reference point? Super important information. This is actually from Oregon State. So I told you guys I love Oregon State, and this is why, one of the reasons we go up there quite a bit. And so this was a really cool sand experiment using height versus time to show how 3D topography shapes the Earth and how different processes sort of conform to it, and really important for learning and that kind of thing. So altimetry measures surface height. Super simple. Above a reference point, you don't need to worry too much about these, but you sometimes hear us going on about these things, geoid, ellipsoid, whatever. You guys don't need to worry about any of this. You just need to know that altimetry gives you height versus time of a thing at a time. And then if you do it at another time, you get the change in height. And that can tell you something about the thing that you're looking at, which is really all it is. And so how do we get all these amazing instruments flying around, orbiting our Earth? Well, we owe it to the insight of some really smart people in the late 60s. It was actually 1968, which is before I was born. So my story doesn't quite overlap with this. And so this is a report that I really urge you, if you're in any kind of altimetry field, or you're a student or an early career person, read this, because this is super cool. It's like the first blueprint that we had for ocean altimetry. It also put forward the gravity instruments that we now see as GRACE. It also put forward SAR. These are like the three main techniques that we use for Earth observing, for solid Earth, for cryo, for ocean. And it's all in this document, like the sort of pattern and what we're going to do. Really, really great. And so NASA sort of ended up launching in the mid-70s an instrument called GEOS. Most of these are launched from Vandenberg, just up the street. In fact, you can see them from Scripps when they launch. They probably saw this. So GEOS was the first one, and then CSAT, which many of you would have heard of, designed primarily to operate over the ocean. Why over the ocean? Well, the ocean turns out is a really simple surface to map with radar altimetry. The waveforms, the return, everything is really well behaved, and you can really understand what you're getting back from it. So that was one of the reasons why, and they put this forward as a technique to map sea level height. Oh, I don't know. Why is it not working? Okay. So GEOS, some of you will have heard of this very, very early days, but it was a big project and got some data, and the quality was actually way better than they thought it was going to be. And in the end, they used the data in a way that was not anticipated before. And so there's a theme sort of that does run through this talk a little bit, which is a lot of these instruments were launched for certain applications, and then the data ended up being used for something completely different, which was really great. And it led to a whole sort of explosion of different techniques and like a sideline of or a sidebar of different technologies. And so GEOS in particular, they discovered that actually it clips the edges of the ice sheets, even though it was in an orbit that didn't go over the ice sheets very much. It just got a little bit around the edges. And remember that word, edge, very key. And it would actually, turns out it maintains track. So people did things with these data, which is really, really cool. I cannot get the hang of this computer. I'm really sorry. Okay, so a sort of an explosion in what could be done, and basically huge potential future for activity, and just this sort of excitement that we actually could have this kind of quantum jump in knowledge, not just in oceanography, but geophysics and ice sheets as well, all sort of like round about the mid-70s. So people started doing this. We know some of these people. We even talked about some of these people at this meeting. They did this analysis in the early 70s, got it published in Nature, like some of the first surface topographic maps. Oh, this is actually the first topographic map ever of an ice sheet. Looks pretty bad, doesn't it? But you know, it was kind of the bee's knees at the time. Like this is actually a 3D plot of an ice sheet, some profiles. We didn't know any of this before. We didn't know the topography of the ice sheet because we didn't have that height. And so people started doing a lot of things with these data. Sorry, this is a really horrible interface for me. Sorry, I'm really sorry. Okay. So for example, CSAT, when it was launched in the bit later in the 80s, very short mission, actually only lasted for 3 months, but it was able to, it went to about this point here, 72 degrees south. So it clipped the top of the Antarctic Peninsula, a little bit of this part of Antarctica here, which is a bit further north than the rest, and provided some really useful data, which could be used to then try and come up with algorithms to do this thing better if we could actually cover in the regions we want to. And that's, in the end, what the data set became that people used to figure out how to put other instruments up and do this properly for ice. So this is, okay, I'll just use this one. Okay, so here we are. We've got to CSAT in the 70s, and then we sort of started to explore. GeoSat was launched in the 80s, and with GeoSat, we ended up having actually a full DEM of Antarctica. Okay, so not full because there's this hole, because that's the orbit limit, but pretty good. Like, so there's actually some topography there that you can see, and this is really nice. We're suddenly starting to see even some like drainage basins and even some outlet glacier sort of 3D formations there. Really foundational stuff at the time. In the mid-80s, this was really cool stuff, like way more than we had before. And then the colors come in. Look at this. This is Jay in the late 80s. We had some slides like this yesterday, these kinds of colors. So Jay was always in, we always got at Jay for his color schemes, but this was probably one of the best. This candy cane cover of sort of stripe map of Greenland, but this is all the individual tracks. And this is basically, as I said, height. That's it. It's just height. So the height of the ice sheet, higher in the middle, lower at the edges. We didn't kind of know all this. We knew that, but we didn't know the actual number until we had the altimeter to tell us that. So this was a sort of foundational point where we suddenly had even topographic maps that could actually then be used for modeling and things like that. Many of you know Uta Hertzfeld. She did a lot of work as well with CSAT and GeoSat and published this atlas. This is actually the first DEM of Amory Ice Shelf, which, you know, this is actually all floating here, and you can see. And what you notice here is there's actually kind of a lot of noise here. So we're going to talk about that because that is one of the downfalls of radar altimetry, struggling in the places where there's topography. So Jay and other people came up with this technique. It's just basically comparing where the orbits cross over. It's just a crossover difference to look for changes in height with time. And they published something which actually ended up being wrong, but it didn't matter because, you know, that's kind of how things go in science. But this was basically the first like intermission height map change for the whole of Greenland. So, you know, Jay was kind of in this territory that we're all in now, but with a very limited data set. And so with these data, what we realized had to be done was examine these data and figure out how to make the algorithms better so that you can get more information from these noisy data. As I said, altimetry was designed to operate over the ocean. This is what you call a waveform. It's what you get back. This is kind of the main thing that you get back from altimeter. It's like the power versus time. And it's kind of a nice shape over the ocean. It's very smooth. Over ice, not so much. Kind of wiggly, kind of a mess, really noisy. So you have to figure out how to interpret this and how to create algorithms that actually give you the actual height that corresponds to the mean surface that you're observing with the altimeter, which turns out it's over quite a large footprint because radar at that wavelength has a sort of couple of kilometers or so footprint. So we have to figure this stuff out. And so Chris Rapley, why is he up there? Well, this is where my sort of storyline intertwines here. I was an undergraduate at UCL in the late 80s, early 90s, and I met Chris Rapley. He actually, honestly, changed my whole career because I was doing maths and physics, and I met him, and he did this class called Physics of the Earth, and it was like, wow, okay, now I get it. And I did a project with him, and he, at the time, this is serendipitous. I mean, I'm very lucky that I landed at the place where he worked at the time they were working on these algorithms. ERS-1 had not yet been launched, but they were all talking about it. I remember the buzz. It was launched in June 1991. I just graduated after that. So I sort of disappeared, but the data were amazing because ERS-1 had an ice mode. So Chris was very involved in understanding these waveforms and really very instrumental in figuring out a lot of this stuff in collaboration with Goddard, with Jay and others. But they really, they published a lot of these. And if you're a PhD student looking at radar altimetry, these reports are really, really useful. There's a lot. They're really thick too. But these reports were so foundational. And then right afterwards, this report came out. This is the first IPCC report. So this is all happening around that time. We're sort of building up the techniques to the point that we can understand the ice sheet. And then we're also getting the first IPCC report, which is telling us that, the Earth is warming and maybe the ice is changing. We don't really know yet. But, this time in the 90s, we didn't really know whether the ice was changing. But we're just getting the techniques ready primed to tell us whether it's changing or not. So this is all happening at all at the same time, simultaneously. So I'm back with this interface. Okay. Okay. We don't need to worry about the details, but if you're a student, you will worry about this. So you can look at this at another time, but it's basically how you get the height measurement, which is the best place on that waveform that corresponds to the mean surface. And, there's some clever things you can do, and you can take a whole class on this, and I'm definitely not going to go into it now. But basically the punchline is, return waveforms for a radar altimeter are different over different surfaces, right? They're really nice over the ocean. That's actually nice. This is nice waveforms. They're narrow peaked over sea ice, and they're kind of a little bit funky shaped over ice shelves because you've got different features there. You've got topography, you've got crevasses, you've got all this stuff. So when an altimeter goes off the ocean and onto land, it starts to get noisy. And that's what we had to figure out and got through to come up with all the algorithms that we use now to get the best heights we can out of the altimeters. And this is another example over a lake where they're really messy and then they go smooth again and they go messy again. So yeah, really important information, but hard to extract. And I looked at way too many waveforms during my PhD. Like I almost never want to see another one again. So this is a time, like right when ERS-1 was launched in 1991, was kind of the time where I talk about it as like a sort of like a splitting or a bifurcation of the branches of altimetry. So CSAT or GEOS before it over here, and then CSAT, and then GeoSat, they were all on the same branch. And then they split off, and we had two different lines of altimetry that got developed. One of them is ocean altimetry, and you all know about Topex and Poseidon and SWAT and Jason, and sorry, Topex, Poseidon, Jason, SWAT, Sentinel-6, all of those, they're all ocean altimeters designed to measure sea level rise. They're in a certain orbit. They only have an ocean mode and all of that. And then there's a second mode, which you've all heard of as well, but they're completely independent. They're actually ESA, European Space Agency. They're not NASA CNES. They're a different group, or different sort of management and everything. And ERS-1 was the first satellite that was launched that carried a radar altimeter. It had everything else on board as well, like a SAR, and a scatterometer and many things. But the radar altimeter was what I'm talking about now. And this was the DEM that came out of that first mission. Here is a bit bigger. So you also see a little hole again, right? Because it's kind of smooth in the middle and there's a hole. That's because ERS-1 only went to 82 degrees south. So everyone knows that the pole is 90 degrees. So it's public lecture, by the way. So I'm trying to, so we have 8 degrees that we still have to go. And so there's a gap. And so there's kind of some smoothing that goes on. A lot of smoothing goes on with altimetry, basically, radar altimetry, especially where there's no data. But where there is data around the edges, you see a lot of interesting information. And now this is a really useful map. In fact, Mattia, I think it was, showed this morning as an input into a model. Having these DEMs are super important because it helps determine where the ice flow goes and all of that. But what you need to do is really figure out how accurate that height measurement is, like how true it is to where the actual surface is. So there's a photo of me there, because it turns out in the end, I did stay on and work on the kind of science that Chris Rapley was doing, but I didn't do it at UCL. I actually moved to Australia and did my PhD in Hobart. And by then, there'd been 3 years of ERS1 data. I had no clue this was going to happen, really, but it was quite good because it meant that 3 years of data had already been collected. I didn't have to sort of wait for the data. And then we actually went to validate the data. And so went to Amory Ice Shelf to do a validation survey with skidoos. And these are our GPS antennas, and we're driving around and we're testing out the actual, or trying to get the accurate height of the surface so you can compare that with the altimetry. And this is what came out of that work, which was mentioned in Shin's generous citation earlier. This was the first map of marine ice under Amory Ice Shelf that we got from the ERS1 map, digital elevation model, and we actually differenced it from radio echo sounding data that had been collected in the 1980s. So that was a really very nice result that we managed to get from integrating the satellite data with the radar, airborne radar. And that kicked off a research program called AMAZOR, Amory Ice Shelf Ocean Research. And these sites were drilled along the borehole. So this is actually thick marine ice. We still use rainbow color scales in these days, so this, forgive me. So this is 190 meters of marine ice along a flow line, and that's underneath the ice shelf. So that's actually observing something that you can't observe directly. It's an indirect observation. And yeah, we were able to then go and drill along these flow lines and make measurements and find out more about what's going on underneath. Okay. Okay, so during this time as well, people use these data to difference with time, or look at height changes versus time. So this was early day height change maps to show us where the ice sheet is changing. Because if you know the height and you know the height has gone down, then you know you've lost ice. If the height's gone up, then you've gained ice. So it's that simple. It's not actually that simple. There are many other things, but that's the bottom line principle. And so again, ugly color maps, not my fault, but you do see that changes over here. This is a change. This is height going down. This is height going down. This is height going down. Duncan Wingham, Jays Wally, Andy Shepard, all sort of pioneers in this technique and showing us how to use altimetry to show us where the ice sheet is changing and point us to places to go. I need to do a time check. I don't have. Huh? Thank you. Okay. So I also wanted to show you results of Topex. Basically, this is a sort of place we were at with Topex at the same time. So Topex, this is from this institution, David Samwell, may or may not be here. And so he used Topex to give us global seafloor topography. So the sort of two branches that split off each led to really cool things in the different areas. And in the end, they sort of come together, and I'll show you that soon. Also, ERS1 was able to give us some of the first sea ice thickness maps. And this is my dear former mentor, Seymour Laxon, the late Seymour Laxon, who was very, very foundational to me in my career, a huge mentor. And he actually came up with a technique for retracking to get sea ice thickness measurements very accurately. And so that it was able to tell us how much ice we're losing, how much sea ice we're losing in the Arctic. And we're working on this still for the Antarctic. And then going into a little bit more back in time, using the ERS1 sort of 1990s to 2000 era data, and then comparing backwards in time to CSAT. So this gave us a good 20-year time series to really try and understand, okay, so we know the ice is changing in a few places, but can we take the record back far enough by going to CSAT to try and figure that out? And we had a paper with Laurie Pavan, another dear, wonderful colleague who I think is online. And he and I came up with, this is one of the first papers we wrote together, maybe not. And this actually showed us changes in ice thickness with time over the whole peninsula, going back all the way to the 1970s. And then this is the work that was referred to, I think, in the citation, some of the work that we've seen today at this meeting. This is changes in the ice shelves from long-term records, basically stitching together a lot of radar altimeter data in one. ESA did a fantastic thing by launching these missions so that they overlapped, and we had this seamless data set of height change from June 1991 until now. Cryosat is still up there giving us, and they've got Crystal coming down the line. So they have this seamless, well-oiled data set from radar altimetry, and we use these data for this one over here on the right. This is Fernando Paulo, who was a graduate student here, now works for Global Fishing Watch. But he learned a lot here to take it to that other useful thing that he does. And then over here, ISAT. Hamish Pritchard came and spent some time here at Scripps in 2011 and did this work looking at ice shelf height with time. And we plotted it on a map of ocean temperature. And what you see there is where the ice is going down, thinning, the red, is where the water is red. So this was the early sort of time, and Eric had published his paper at this before then as well. And we kind of knew this basal melting is driving the changes and the ocean is driving the ice shelf changes. And so this was sort of seeing it all coming together from this one instrument. And then we did a little bit more, which is going into, this is back to Bryony's technique that she was talking about earlier today, if any of you saw it, but using, once ISAT was up, ISAT was kind of the next thing where, okay, so radar altimetry is great, but radar altimetry struggles because of the fact it's a large footprint, and laser altimetry is very, very, it's a much shorter wavelength. It's a laser. It has a few cons, of course, because you can't have all pros. It is affected by clouds at that wavelength, but the pros are that the footprint is a lot smaller, so the height ends up being a lot more accurate. And we were able to look at changes with time over the grounding line and pull out this flexure, this flexing area that Bryony was talking about earlier. And that is where we went into the side quest. So the side quest was mentioned in the citation as well. So when I was looking at the grounding line of Ross Ice Shelf, one of the first tracks actually was right here, track 53, my favorite track of ISAT. And what we found was right upstream of the grounding line, there was this crazy signal that everybody looked at and said, oh, no, that can't be right. No, you must have made some problems. You've got some problems there. No, couldn't possibly have like 10 meters of drawdown or change in like, but anyway, long story short, it wasn't wrong because we actually looked at all the cross tracks and the same signal was there. This is the discovery of the active subglacial lakes from laser altimetry. I have to say, I was not the first person to do this. There was actually radar altimetry looking at using crossovers, looking at some lakes upstream in Adventure Trench. And then before that, actually, Lawrence Gray had used SAR to identify some lakes. But it was the first sort of active system of lakes found underneath an ice stream. And the fact it's under an ice stream is super key because that can change the subglacial hydrology and the flow dynamics and that interaction. And I love the whole concept of this because it was a new process we didn't know about before, and also not a climate change. It's not, oh, you know, this thing is changing because of climate. It's actually a process that was new that we discovered. So that triggered another whole load of field work. There's two sets of field work for this one, actually. So Wizard, some of you remember that, and then Salsa. I'm not going to spin off those acronyms. But anyway, they were drilling projects into these subglacial lakes on Willan's Ice Stream, and a lot of people involved in this, really super interdisciplinary project. I've given like a whole hour lecture just on this alone, so I'm not going to spend much more time on this, but super exciting. There is actually a movie, The Lake at the Bottom of the World, about the Salsa project. Very exciting project to be part of. But it was definitely a side quest for me. I'm not really in lakes anymore. I'm back to ice shelves. I enjoyed it for a decade, but ice shelves are kind of my thing. I think it's hard to get away from them. Okay, so in the sort of 2010 era, we have these new missions. So I already told you about ISAT a little bit, and then also Cryosat. So Cryosat was ESA's big new thing, shiny thing. So two big new shiny instruments had sort of been operating. ISAT was earlier in 2003. Cryosat, well, the first Cryosat wasn't so successful. This is actually Cryosat 2, but got rebranded. And so why were these so innovative? Well, Cryosat was able to kind of improve the resolution of the footprint and give us better information along track by using a very clever interferometric processing technique that Duncan Wingham wrote lots of papers about, and lots of people don't understand them, but it's very, very smart and produces really great data. We've seen some this week, actually. And then ISAT, this laser altimeter from NASA. And then ISAT-2 came along in 2018. So these are the sort of sequences of instruments that I've been working on. In fact, the whole reason I came to the US was to work on ISAT. It hadn't been launched yet, but I came as a postdoc to work here at Scripps with Bernard Minster. He was on the science team. So this mission actually brought me from Hobart to San Diego to work on the new data, because radar altimetry, you know, there were flaws. We really thought ISAT was going to like solve all our problems, and it sort of did, but you know, then it brought others. So yeah, Cryosat. Cryosat has done a lot. I didn't want to miss out Cryosat. Cryosat's just a fantastic instrument, but I haven't spent so much time in my career working on that. But I didn't want to miss it out. We have still been looking at a lot of long time series. This is some early work that Sushil did when he was a student here. You've just heard from Sushil today. So yeah, looking again at long time series of all of these radar altimeters put together to try and understand the processes driving the changes, and then going into more, I don't think, did Sushil show this map? I can't remember. I actually had to duck out for a minute, but this was his amazing map of basal melt rates. And a lot of people have been talking about this at this meeting. And so the next step from just looking at height versus time is actually convert that into something that can be useful for modeling. We actually talked to Sophie Nowicki and asked her at a sea level change meeting here at Scripps, actually, like, what do you guys need from us? And she said, Sophie Nowicki is an ice sheet modeler, runs the ISMIP program. And she said, we need melt rates. We need melt rates on a plate. I said, okay, we'll give you melt rates on a plate. I'm like, can't you just take the heights and multiply them by the ice shelf areas? She's like, no, we want melt rates. So Sushil worked out a way to give melt rates. And this is our melt rate map that they have subsequently used. And I know it's not the only melt rate map, but it's one of them. And so it's really sort of shows you what you can do with a long time series of data. Other data sets went into it, of course, but the altimetry was the sort of driving force for this particular melt rate map. And then on the right, we've seen this map a little bit as well at this meeting. This is what happens when you difference the later ISAT mission, the ISAT-2 mission, from ISAT. So this is 16 years of change from one mission to the other. In this map, we've actually used an intuitive scale. People have started using this much more intuitive scale, which is red is loss, which is hot. It's just like your faucet or your tap on your sink, very easy. So red is loss and blue is gain. Blue's cold, red's hot. And so this is the New York Times rendition, actually. The color scale is different to the one we had, of the map from the Smith et al. Paper. So this is now showing us where the ice is coming off Antarctica the most, where the height is going down the most, and we can focus on where the changes are. And you'll notice that it's all around the edges, which is going to bring me into the next part, which is the final part. So it says I've been going for 53 minutes, but that's not right. Okay, good. Thank you. Okay. So the game just kicked off, be fully aware. Don't tell me the score. Okay, and so ice is being lost around the edges of Antarctica, and why does that matter? Okay, so on the left, you see sea level contribution, how it's changed with time. The little colors in the pie chart tell you where it's coming from, because sea level change doesn't just come from the melting of ice sheets and glaciers, it also comes from thermal expansion. So the red is thermal expansion. This is with increasing with time. The size of the circle is increasing with time because the whole signal is increasing with time, but so is the proportion of Antarctica to the whole. So by this time period, we have 10% of the ice loss, or 10% of the signal of sea level rise coming from the ice sheet, the Antarctic ice sheet, whereas back in the 70s, it was a really small amount. And so we know that we've got this possibility for that to become a very large number. And we've heard about this today. And Mattia actually already showed one of the figures I'm about to show. And a couple of people talked about this. So Eric talked about recovery, having a huge sea level potential. I mean, the darker the blue on that map, the more sea level is behind it. So you really want to worry about the dark blue areas in Antarctica. I'm not saying you don't want to worry about the West Antarctica, but for me, East Antarctica is a focus of huge concern because of the potential sea level coming from it. This is a map that Mattia showed, actually a slightly different version, but from a paper we had last year now, showing how the future is very uncertain in terms of how much ice will be lost from Antarctica. So we have to learn it. We have to understand it better. We have to observe it better. Back to the map. Why is it so tricky? Okay, so around the edges of Antarctica, margins, where all the changes are happening, this is what it looks like. It's a hot mess. Okay, well, it's a cold mess, but it's a mess. And basically, an altimeter is going to really struggle over this area. Even a laser altimeter that is able to get a small footprint, and it's still going to struggle because there's a lot going on. There's a lot of topography you've got to try and unravel. Those height changes with time are now getting really complicated. Okay, so you've got to try and capture all of this, and very hard. And these are the scales of change. We already talked about grounding zones today, and all these things, pinning points, they're all super important, but we don't map them at the right spatial and temporal scales to understand them, to be able to put them into models, because we just don't have that information yet. And so, yeah, I'm not going to show this, but this is another map that was, well, I am going to show it, I guess. This is another map that was in our science papers showing like the mass loss processes from Antarctica, the calving and the melting are all getting down to time scales and spatial scales that we don't yet observe at. Things that we've heard about, like today in this meeting, like turbulence and eddies and things like that are just not captured. And so, you know, if you're observing features that are responding to processes like that, then you're not going to be able to sample them well enough to fully understand them. And so this is the problem. So here we have basically your typical sort of ice shelf with lots of rifts and things, ERS1, wide swath, ISAT, a little bit wider, ISAT2 a little bit smaller than that. They get smaller, but they still encounter a lot of topography. And basically, you're going to struggle. The altimetry noisy data does get really noisy. I'm trying to go fast because I know about the England game. And so ISAT did solve a lot of problems. It gave us some really useful data over rifts. ISAT2 even better because the ISAT2 sort of innovation was to go from a single beam sampling, which is just one strip going around, is a red laser. And so the analogy I like to use is like, it's like wrapping a piece of cotton around a ball. That was ISAT. ISAT2, we realized we needed more information across the track. So ISAT2 used, split the data into 6 beams. It was 3 pairs of beams. And that's a bit like having 6 sets of, say, wool, thicker, going around the ball. You're going to map more, you're going to get more information, but you're still going to have a lot of gaps. I'll tell you about edge when we get to edge. And so but ISAT2 was great and is great. It's still collecting a lot of data. And we have a lot of information and a sort of like a hint at processes that we could learn more about if we were able to sample at higher spatial and temporal resolution. For example, this is a whip round, so hold on. This is a Marie ice shelf, favorite ice shelf, before and after calving from ISAT2. Information about rifts, information about melange, all sorts of things in there. Suji Wang at Penn State has done some amazing work with ISAT2 over rifts. This is some of her work, also on Amory. The details of the rifts here is beautiful, but you know, there's just this limitation in how much you sample because of the gaps in the data. Suji Wang again, lots of information here. I'm not going to talk about it, but basically to tell you that ISAT2 is very good at giving you information where there is data, but there are a lot of gaps in the middle where you want to just fill in, but you can't just interpolate. Thwaites, really nice data here looking at pinning points, because we know pinning points are super important. We've heard about those today as well, mapping those, how they're changing with time. And this was Bertie's pinning points paper that we've heard about as well. Learning and looking at pinning points, how they're changing. You need the high spatial resolution, and it's really good while you have it, but there are gaps. Catherine's paper looking at Conga-Glenser ice shelf over here near Shackleton made use of a lot of ISAT2 data as well, giving us some knowledge and getting us to understand the processes, but just not quite giving us enough. The gaps. So here are the gaps. So here's ISAT2 gaps. There's like more gaps than data, right? Like I shouldn't go on about the gaps because ISAT2 is amazing, but we need better sampling. And so basal channels, also really important. We've heard about these today, and ISAT2 is able to give us some really nice data looking at changes in basal channels with time, and the channels actually funnel the melting and give us higher melt rates, and we can look at that. And Cecile talked about this as well. But you know, the spatial resolution again is the issue. I'm going to jump over that. ISAT2 also does basal melt rates. ISAT2 does one thing that EDGE is not able to do, and that's because it's a green laser and it penetrates through water. And so we got some very nice information about melt lake features from ISAT2, which is, yeah, just sort of still a bit of a work in publication, but it's a very nice data set. If you want this data set, let me know. We can get it to you. And then work with Roland Warner, who I think is online, looking at a dough line on Amory again. Told you, favorite ice shelf. And this is very nice, also looking at ISAT2, but pointing to this limitation in spatial and temporal sampling. So, you know, we really want to understand the ice shelf region very well around the edges, at the margins. The grounding zone is really important as well. We heard this all morning from the sessions. And grounding zones are very well sampled as well by ISAT2. We heard this from Bryony, and I had showed you earlier from the ISAT. And so ISAT2 has been able to pull out some really nice information about tidal migration. This is a 10 or so kilometer tidal migration that Bryony talked about earlier. This is a lifting of the ice shelf with ocean tide. And then this other work that Bryony has started and talked about today, which is the viscous bump at the grounding line, which tells us about basal drag and ice viscosity as well. So this is all coming from ISAT2. I'm going to just jump through this. This is information about lakes. We have a lot of data from ISAT2 telling us about lakes as well. This is from Matt Siegfried, and Mike showed this earlier this week, but the really improved sampling is great, but not quite at the place where we need to be to understand. So I'm going to tell you about EDGE in a minute. Atmospheric rivers, ISAT2 gets data from the top of the snow, which is very nice because you actually can pull out snowfall events. So these atmospheric rivers, which are becoming what we think is more frequent over the ISAT2 period, adding to the mass overall on the ice, on the whole ice sheet, and we can pick that up with ISAT2. So ISAT2 does not just do ice, it also does a lot of other things. So this is kind of the whole new way that NASA is kind of being split up into the cryosphere and the biosphere and other things. So we obviously do a lot in the cryosphere. We also do a lot in the biosphere as well, because ISAT2 is able to give us information over the forests and the trees and vegetation. It also gives us bathymetry, and it also has been able to monitor human reservoirs. So the point being, the key thing here is it's monitored changes across the full Earth system. There's also in parallel another instrument on board the International Space Station called JEDI. And why am I talking about JEDI? Well, you'll find out in a minute. JEDI is a great instrument. It's at the infrared wavelength, so it's not the same as ISAT2, but it's on the space station, so it's constrained in its orbit because the space station does not go around the poles. It just goes to 50 north and south. So we are working with the JEDI team. But before I get there, I'm going to show you the highlights of ISAT2 and do another time check. 15 minutes left. Okay, so this is the movie of ISAT2 and showing us how the data build up with time. This is I showed you the still of this at the beginning, but this is, I think, an amazing visual showing us how you can use these data to understand how these different parameters have changed with time in the Earth system from the launch date of ISAT2 in 2018, and this goes until 2024. So you can actually get this from the NASA Science Visualization Studio. This is mean forest height on top of mean terrain height, because you can extract the tree height from that. Okay, so I got to move along because I've got to get to edge. What have we learned? Okay, so from the ocean altimeters, we've learned that sea level is going up with time, right? We know this. This is TOPEX, JASON, the Copernicus mission set, Michael Freilich satellite. This is an increasing signal. It's actually accelerating. These are all the ocean altimeters, and this is a signal that they have produced. At the same time, we've had this parallel branch of altimeters mapping change in ice with time. And we made this map. Jennifer is here, made this amazing map that kind of went together with the ocean altimetry one to show us the change in ice with time. This is just the altimetry contribution from IMBY. IMBY also brings together the SAR, the input-output method, and the GRACE. It's a fantastic sort of consortium of all the different techniques that all work together to complement each other. But my point here is to show you that these different altimeters have shown us sea level rise in parallel with ice sheet melt, but different instruments, independent, but all coming from the same technique. And the sea level change team is a great group, a big NASA sort of interdisciplinary team where you can go at sealevel.nasa.gov and you can get these metrics of like what is happening with sea level now, ocean mass, Greenland mass change, Antarctic mass. I encourage you to go to this. It's a fantastic resource. I'm going to jump through this. You all know about SWOT. SWOT has basically done a lot for understanding processes around the edges of the ice sheets in the ocean. If you don't know about SWOT, you should. And I think Tasha is probably going to talk about SWOT tomorrow or Friday. There's also some really great data over the ice shelves as well. But this is the sort of next generation ocean altimeter that kind of comes along with ISAT2 and JEDI. We're sort of where we are right now, the current state of the art. So I'm going to talk about the future for about maybe 8 minutes, and then we'll be done. So the future is bright, hopefully. So coming down the line from ESA, we have this mission called Crystal. Not the Seligman crystal. It's actually got an I in it, not a Y. And Crystal, I can't remember what it stands for, but anyway, it's coming and it's going to be great. It's a dual band radar altimeter, and it will be launched in, well, the website currently says 2027. So next year. So that's great. So ESA have something in the pipeline. So what is next for NASA, you might ask? Well, I'll tell you. In February, we were selected, EDGE was selected for implementation. It went through a 2-step process with NASA. A lot of work, a lot of work. I kind of didn't do much else for a long time. Basically, it's a joint project between the Terrestrial Ecosystem Group and the Ice Elevation Group that you talked about. It's kind of like bringing JEDI together with ISAT2 and moving it into a free-flying orbit, a free-flying instrument in a free orbit, polar orbit. And so I can't do that by myself because, I only do ice altimetry. So obviously don't do the instrumentation either. So we, of course, need to go to the gurus for this. So at NASA Goddard, we have Brian Blair, who leads the Elvis facility, and then Scott Lufke, who's a geodesy guru and just all-around amazing human. These guys are amazing, worked on so many different missions. And then John Armstrong, also amazing, probably online. John is the deputy PI for ecosystems. He works on Jedi, and I needed help. I love trees, but I don't know much about them, so I needed the help. And so we are the team. We are the interdisciplinary team. We were interdisciplinary from the get-go. Edge was designed to be a community instrument for the entire Earth system. Well, starting with just ecosystems and ice. Okay, so I'm going to give you a very quick lightning talk of what Edge is. So Edge is it's evolution. You have to show evolution with NASA, but it's also continuity, because we really do need the continuity. I think I've told you or like given you the reason why we need to keep monitoring the ice sheets with altimetry. Well, we are going to continue doing that, but we're also going to innovate by going way higher resolution. Edge is a a swath mapping instrument. It's an imaging, so Jedi and ISAT-2 are multi-beam, and Edge is a swath mapping. It's basically like an imaging LiDAR. So it takes things to the next level. So here's this is our cotton. These are our wool going around the Earth. This is like ribbons going around the Earth. You can cover the ball very quickly with ribbons, and that's what Edge is going to do. And so how does it work? Well, it's basically got 5 lasers, and each of those lasers is split into 8 beams. And so on the ground, these are 120 meters wide. And in between the strips that we call the mini swaths, there's 1.2 kilometers. So it's a really big swath, and the coverage is amazing. Basically, it takes away the whole need for really repeat tracks, because you have so much coverage. And we're going to be able to show a lot about what's happening around the edges of the ice sheets. We have this sort of strategy behind our implementation. We're teaming up with what used to be Maxar. They went through a couple of name changes. Now they're Intuitive Machines up in Palo Alto. It's the same spacecraft that's used for the Worldview Legion high resolution imagery. It's stable. You need a stable, precise platform, high accuracy. It's agile. And we do that. We need that because we have a capability to target. It's the first time that that's been a possibility for an altimeter like this. And I'll show you that in a second. And the orbit is sun synchronous. We've gone back to sun sync. We are not going all the way to 88 like ISAT-2 and CRISAT. And that's okay, because what we do is we actually place the highest density tracks over the edges of Antarctica. So the margins. So yeah, I mean, in the end, you get better spacing in the places where you need it the most. And so that was kind of, in the end, a really nice thing that came out of this collaboration with the vegetation group. And we also have the lowest altitude over the equator, because you have thick tropical rainforest there, and you need dense, to improve the link margin. These are our modes. I won't go through this. I can definitely talk a lot more about Edge if people want to know more, but we do have the first time sort of rapid targeting. We can dwell, we can spend longer on a place. If you love a glacier, we can spend more time there for you. Who knows what you're going to want in 2031. Maybe we'll be back here even in 5 years, and you can tell me. Transformative science. Well, okay, so we're kind of going for the major issues. This was in the slide deck right from the beginning of when we first started working on Edge in 2021. Forest fires, sea level rise, super important. I already showed you the tipping points. The tipping points are really well sampled by Edge. We actually get all of these things. We get the boreal, which Jedi couldn't get. And we just able to increase the coverage by the width of this hourglass tells you the coverage. ISAT-2, as you can see, super thin, Edge really thick. So yeah, much better sampling. And we will, because of that, I'm going to jump through this, but trust me, it's all grounded in the decadal survey, which we heard about from Brittany. We have possibility to do fire and carbon and snow and permafrost. But this is now a big whiz through, because I really want to get to the end. So measurement gaps were thought about for a long time by the science team. We thought about what we have up flying now. We have Jedi and ISAT-2 that are flying at the moment. What can they sample with what they do, right? Their sampling is limited, but they are able to do a lot. They tell us a lot, but there's some things they can't get. Like, for example, I'll just look over on this side because you're all familiar. So the rifts and the ice fronts are undersampled. The grounding zones are undersampled. The basal channels are all undersampled by ISAT-2, but Edge is going to get them all. And let me show you. So this is actually the best way that we've come up with to show you how amazingly wow factor Edge sampling is going to be. So look at these 2 circles. They're 20 kilometers in diameter. Jedi on the left over the Amazon, and ISAT-2 on the right over the Cook Ice Shelf at 68 degrees south in East Antarctica. Super important outlet glacier. But look at all the white space on the ISAT-2, and now look at what EDGE will do. Fills in everything. Wow, all those crevasses pop out, and it's kind of amazing. And it's similar story in the Amazon, where you can now start to see a forest emerging. Things you can do with that, I won't go into, but trust me, forests are needed for habitat, which are needed for animals, which is megafauna, and we have orangutans in the EDGE proposal. We also have this fantastic capability to be able to bring all the swaths together and map a very high resolution along spatial resolution with a mega swath along the coastal corridors. The ice, well, we've heard about the basal channels. I already showed you. Basal channels are just going to be amazing in EDGE. So you can't even tell that there's tracks under here because the EDGE data are so good. We use gold for EDGE in the proposal because we're going for the gold standard science. Some of you know what that means, right? So we kind of went for that. So the gold is under here. The ISAT-2 is in blue. Not very good coverage. So much better information with the EDGE data. We're going to be able to understand the pattern and the change and the shape of the rifts and the interacting with the basal channels as they're forming in a really coherent way as EDGE is flying. And the same over here again, Amory Rift and how it's really well sampled with EDGE. We also have baby penguins. So yeah, sea ice, again, it's really great for picking out the leads, much improved sampling, improved lead detection, and all the information that's needed for sort of sea ice modeling. I'm going to jump through. I do have a movie, but I don't know if I have time for it. Maybe I do, 5 minutes. And this is basically showing you the targeting mode of the instrument, which is just, we actually made this for the AGU meeting, and we ended up showing the region where AGU was held. You'll notice the red, white, and blue spacecraft. Yeah, so anyway, I think I won't show this whole thing. If you're interested, I can show it to you another time, but not right now. Okay, but what have I done? What have I done? Okay, so there's a thing at NASA now, it's all about Earth action, right? And so the data that we are going to collect by EDGE is what we call actionable. That means it does something useful for society. It's kind of a commitment to, and you might wonder how on earth did they get this selected right now? Well, this was the kinds of things we talked about because everybody needs to understand the height of the Earth and how it changes with time. No matter what side of the aisle you sit on, in politics, you need to understand this. And so situational awareness, national security, food security, resilience, all of these things, we had over 70 letters of commitment for the mission. And we sort of argued that it will help the US, but also the world, efficiently manage resources and safeguard our citizens. Many incredible applications here. Just look at this middle one, which is color-coded by how quickly people need the data. So if it's in a dark gold color, you need that data pretty quickly because flooding happens pretty fast. Whereas insurance and things like that, maybe you can wait a little bit longer. But all of these sort of agencies and outcomes and stakeholders will use the data eventually. High value to the nation. We talked about this yesterday. You need to be able to show return on investment for NASA missions. And this is the wonderful Jim Garvin, who's a Da Vinci PI, did this study for us using an AI-based approach to show us the return on investment as the data are sort of the uptake in data after the launch in 2030, which I think I didn't tell you all, September 2030. And so in 8 years' time, the return on investment is modeled to be 50 to 1, which is a huge value. Okay, so I'm nearly finished. This is the 50 years of laser altimetry on a sort of full family tree, starting with that Williamstown report, going to the GRC, so all these branches split, we come down, all the ones we know now, ISAT-2 Jedi, here's EDGE, here is where it will fit, Crystal as well. And I thought I'd throw in the timing of the IGS meetings, because that's kind of interesting. Last IGS meeting, we didn't have ISAT-2 flying even. So that's kind of amazing. And by the next one, hopefully, well, here we are now, because we have this gap, of course. You know, EDGE is like now about to be, well, we're starting to build it. In 4 years' time, it'll be launched. So the next World Cup will be actually ready to launch. And by the time we have the next meeting here, we should have been on launch for 6 months. So you guys need to keep me in check on that one. Okay, so we've learned a lot. This is our we call this the knowledge steps. ISET sort of was a pathfinder showing us a little bit of info, and we're learning more. I love this way of thinking about it because we really sort of think about what we've gained and things that we can actually do with the data once we understand the processes better by observing it better. I have a poster on this that you can look at more. So I'll just wrap up with this. We need to be able to tell the community the work that we work on. Right, this is so important. We are very lucky to work in the field that we work in, and we need to communicate our results. This is an incredibly important statement by Jane Lubchenco. If you don't know her work, please go and have a look at some of her papers, because she talks about the sort of stewardship that comes with being an earth scientist. I am going to quickly say, don't get distracted by the false promises of geoengineering. If you want to see a paper on that, we have a paper led by Martin Siegert that came out, but there's a poster outside which shows what I call the action wheel. This is kind of the things that the community kind of probably needs to focus on in the future. And these are the distracting things like diverting attention and all these things. This is kind of the where I think personally the value is. So we can argue about that, but I'll finish with this, which is a summary. Obviously, we've got this incredible record. We've learned a lot about the Earth's vital signs since the 70s. We've just had a lot of people involved in all of this, collaborations and missions that have been planned for years and led to some incredible data sets that have all just led to this advance of understanding. Future missions will probably, hopefully, improve things even more. And I'm going to end with a thank you. And please tell me what the score is. I should say thank you to everybody for everything, because, this is all a massive team effort, and friends, family, colleagues, you're all amazing, and just keep going because, we're doing important stuff. So yeah, thank you.
Thank you very much.